Okay, so for FRK number 6, we have a 4 kilogram particle moving along the x-axis, and its position is given by this function, x of t is equal to t plus 2t to the power of 3, where x is in meters and t is in seconds. Now part A wants us to find the kinetic energy at any time t. Okay, so if we want to find kinetic energy, we first need to find the velocity function. And the velocity function can be found by deriving the position function. So as a reminder, x of t is equal to t plus 2t cubed. If we derive this, we will get v of t, and v of t is going to be equal to derivative of t is 1, derivative of 2t cubed. My 3 becomes my coefficient, then times 2, so 6. And then I subtract 1 from my exponent, so t squared. And then this is in meters per second. So this is my velocity function in terms of t. Now that I have this, I can find my kinetic energy function in terms of t. So Ke of t is going to be equal to 1/2 times v times velocity, and that's where I plug in my velocity function, v of t squared. Okay, so mass is 4 kilograms, and I'm going to plug in 1 plus 6t squared for v of t. So 1 plus 6t squared, and then square all that. 1/2 times 4 is 2, and now I'm going to square, basically expand this, which is going to be equal to 1 plus 12t squared plus 36t to the power 4. And so if I distribute my 2, my Ke function, Ke of t is going to be equal to 2 plus 24t squared plus 72t to the power 4. And this is in terms of joules, and this is my kinetic energy function in terms of t. Alright, part B wants us to find the acceleration of the particle and the force acting on the particle at anytime t. So what they want us to do is find the function for A of t, for acceleration and force in terms of t. So first of all, for acceleration, what I have to do is take the derivative of velocity. So as a reminder, my velocity function is 1 plus 6t squared. So if I derive this, I'm going to get velocity function, which is so the derivative of 1 is 0, so this term cancels out, and the derivative of 6t squared, I take the 2 out and multiply by 6, so 12t, and then my exponent decreases by 1, so t to the power of 1 is just t. So this is my acceleration function, and the units is meters per second squared. Now for force. Force is equal to mass times acceleration, so F of t is going to be equal to m times the acceleration function, A of t. Mass is 4 kilograms, and I'm plugging A of t, which is 12t meters per second squared. And so if I distribute So basically, if I multiply these two, my force function is going to be equal to 48t, and this is in terms of newtons. So, all right. Part C now wants me to find the power being delivered to the particle at time t. So make a function for power in terms of time. So power, first of all, is equal to work over change in time. Work is equal to force times the distance, delta x. And so delta x over delta t is velocity. So power is going to be equal to force times velocity. So that means that P of t is going to be equal to my force function times my velocity function. And I'm plugging them in right now. My force function is 48t newtons. My velocity function is 1 plus 6t squared, and then meters per second. If I distribute this 48t to each term in the velocity function, my power function turns out to be 48t plus 288t cubed, and the unit is in watts. So this is my power function. Now part D wants me to find the work done on the particle in the interval t equals 0 to t equals 2 seconds. Alright, so work is a change in kinetic energy. So what I can do is I can find kinetic energy using this formula at the 2 points I want to find, and subtract those two. So first of all, I want to find Ke at t equals 0 seconds. And then, so I'm going to plug in 0 for every t in this function. So 2 plus 24 0 squared plus 72 0 to the power 4. Plugging into the calculator, I just get 2 joules. Now for my Ke at t is equal to 2 seconds, I plug in 2 for every t. So 2 plus 24 2 squared plus 72 2 to the power 4. Plug this in the calculator, I get 1250 joules. Alright, so as I said, work from 0 seconds to 2 seconds is the change in kinetic energy. So Ke at t equals 2 seconds minus Ke at t equals 0 seconds. So I plug in these two in, 1250 joules minus 2 joules, and so my work is 1248 joules. Alright, now part E asks, does the particle turn around at some point and head back to the original position, and clearly explain why. So if I'm looking at whether the particle turns or not, I'm going to be looking at my velocity function. So here's my velocity function. V of t is equal to 1 plus 6t squared, and t should be greater than or equal to 0. So if I plug in any value from 0 to infinity, I'm always going to get a positive answer. So that means my velocity is always positive, meaning it will always be going to infinity and never be turning back to the origin. So here's my explanation. velocity is always positive for t equals when t is greater than 0. Velocity is never less than 0, so the particle will not turn around ever to head back. Sorry, this is around here. Around ever to head back to its original position, and will keep on going farther and farther away. And we're done.